Hello, fellow dreamers of space exploration. And to all the researchers shaping the future. Today, we embark on an extraordinary journey, exploring groundbreaking ideas that will propel SpaceX's Starship even further, expanding humanity's reach into the cosmos. Starship has shown us the potential to venture into space, but challenges remain for deep space missions like Mars exploration. One of the most critical challenges is improving the performance of the heat shield. The immense frictional heat generated during Mars' atmospheric entry poses a significant threat to Starship. Protecting the spacecraft from this extreme heat is the heat shield's primary function. Therefore, today, we will introduce 6 key technologies that could revolutionize Starship's heat shield. This isn't mere fantasy, it's a realistic science fiction, based on current scientific principles, combined with future predictions and imagination. While the technologies presented here are not yet a reality, we hope this imaginative exploration will inspire researchers and offer viewers a glimpse into the infinite possibilities of space. So, let's delve into 6 key technologies that can revolutionize Starship's heat shield. Graphene-Lattice Ceramic Composite. Description: this is a new material combining graphene's exceptional strength with ceramic's heat resistance. The key is creating graphene in a nanoscale lattice structure to achieve even higher strength and thermal conductivity. Ablative polymer matrix with heat dissipation nanoparticles. Description: ablative materials protect spacecraft by absorbing heat and vaporizing. Adding heat-dissipating nanoparticles maximizes heat dissipation efficiency. Quantum entangled alloy. Description: this hypothetical alloy utilizes quantum entanglement to maximize interatomic bonding. Theoretically, it could possess extremely high strength, flexibility, and unique electromagnetic properties. Bioregenerative life support system. Description: beyond simple air, water purification, this system uses biological, ecological principles with plants and microorganisms to autonomously produce oxygen, water, and food within the spacecraft. Atmospheric CO2 scrubber with 99.9% efficiency. Description: this high-efficiency device can almost perfectly remove carbon dioxide from the atmosphere. 99.9% efficiency significantly surpasses current technological capabilities. High-temperature superconducting coils. Description: these coils maintain superconductivity at high temperatures and play a crucial role in generating powerful magnetic fields and confining plasma in fusion reactors. This technology would be essential if Starship were equipped with a fusion propulsion engine. Now, let's explore the development methods of 2 of these technologies in detail: graphene-lattice ceramic composite, and ablative polymer matrix with heat dissipation nanoparticles. Graphene-lattice ceramic composite manufacturing method. Key strategies: precise lattice control, minimizing defects and maximizing uniformity in the graphene lattice. Strong interfacial bonding, maximizing chemical, physical bonding between graphene and ceramic. Optimal heat conduction path formation, designing a structure that efficiently dissipates heat flow. Manufacturing process: a high-quality graphene lattice fabrication. Substrate selection and pretreatment. Single crystal copper, Cu, or nickel, Ni, foils are used as substrates, undergoing electropolishing and annealing to remove surface impurities and control grain size. Low-pressure chemical vapor deposition, LPCVD, carbon precursor. Methane, CH less than sub greater than 4 less than, sub greater than, ethylene, C less than sub greater than 2 less than, sub greater than H less than sub greater than 4 less than, sub greater than, or acetylene, C less than sub greater than 2 less than, sub greater than H less than sub greater than 2 less than, sub greater than, gases are used. Deposition temperature: 900 to 1000 degrees Celsius, optimized depending on the substrate and precursor. Pressure: 1 to 10 torr. Gas flow rate: precisely controlling the H less than sub greater than 2 less than, sub greater than, CH less than sub greater than 4 less than, sub greater than ratio and AR dilution gas flow rate. Growth time: adjusted for single-layer or multi-layer graphene formation. Lattice formation: electron beam lithography, EBL, and reactive ion etching, RI. Desired patterns are formed using EBL, followed by Ri to remove unnecessary graphene, creating precise lattice structures. Self-assembly-based lattice formation. Functionalized graphene nanosheets are dispersed in a solution, and large-area uniform lattice structures are formed using Langmuir-Blodgett (LB) film formation or solvent evaporation self-assembly. B. Ceramic matrix integration. Atomic layer deposition (ALD), or molecular layer deposition (MLD), ceramic thin films such as alumina, Al less than sub greater than 2 less than, sub greater than O less than sub greater than 3 less than, sub greater than, zirconia, ZRO less than sub greater than 2 less than, sub greater than, or titania, TO less than sub greater than 2 less than, sub greater than, are precisely deposited on the graphene lattice in atomic or molecular layers. This ensures uniform film thickness and excellent interfacial adhesion. Enhanced penetration. If necessary, an impregnation process using a ceramic precursor solution can be added to fill the graphene lattice with ceramic. Supercritical fluid or high-pressure impregnation techniques are used to maximize penetration efficiency. Subsequent heat treatment. A heat treatment process is performed at appropriate temperatures and atmospheres to strengthen the interfacial bonding between graphene and ceramic and improve the crystallinity of the ceramic thin film. Rapid thermal annealing, RTA, or laser annealing techniques are used to minimize graphene damage. Quality control. Raman spectroscopy, transmission electron microscopy, TEM, scanning electron microscopy, SEM, analyze graphene quality, defect density, number of layers, lattice structure precision, ceramic thin film thickness and uniformity, and interfacial bonding status. Thermal conductivity measurement. Measure the composite's thermal conductivity using the laser flash method or the 3-omega method and optimize it by comparing it with theoretical predictions. Ablative polymer matrix with heat dissipation nanoparticles manufacturing method. Key strategies. Uniform nanoparticle dispersion, preventing nanoparticle aggregation during the ablation process. Strong interfacial bonding, maximizing the adhesion between the polymer matrix and nanoparticles. Optimal heat dissipation characteristics implementation, optimizing ablation rate and heat dissipation efficiency. Manufacturing process. A. High-performance nanoparticle manufacturing and surface modification. High-purity nanoparticle synthesis. High-purity nanoparticles such as diamond, boron nitride, and silicon carbide are synthesized using chemical vapor synthesis, plasma synthesis, or laser ablation. Surface functionalization. Silane coupling agents, titanate coupling agents, or polymer grafting are used to modify the nanoparticle surfaces. This induces chemical bonding with the polymer matrix and improves dispersibility. B. Polymer matrix synthesis and nanoparticle dispersion. Solution mixing or melt mixing. High-performance thermoplastic polymers with excellent thermal stability, e.g., polyimide, phenolic resin, are dissolved or melted in a solvent. Then, surface-modified nanoparticles are added and uniformly dispersed through high-speed stirring or sonication. Shear thinning induction. Additives with shear thinning properties, e.g., clay nanoparticles, layered silicates, can be added to improve the dispersion stability of the nanoparticles. C. Composite molding and post-treatment. Extrusion molding, injection molding, or 3D printing. The melt-mixed composite material is fabricated into desired shapes using extrusion molding, injection molding, or 3D printing. Cross-linking or curing. If necessary, chemical cross-linking or thermal curing processes can be used to improve the mechanical strength and heat resistance of the polymer matrix. Quality control. Transmission electron microscopy, TEM, scanning electron microscopy, SEM, X-ray photoelectron spectroscopy, XPS. Analyze the size, shape, dispersion state of the nanoparticles, and the interfacial bonding state with the polymer matrix. Thermal analysis, TGA, DSC, DMA. Analyze the thermal stability, ablation characteristics, and mechanical properties of the composite material. Laser ablation test. Directly evaluate ablation characteristics using a high-power laser and optimize by comparing with theoretical predictions. These revised manufacturing methods are more realistic than previous versions and reflect additional considerations derived from detailed analysis. In particular, by clearly presenting the process variables for each step and specifying quality control methods, we have aimed to make them more helpful for actual research and development. If all 6 technologies described above, including Graphene-Lattice ceramic composite, and Ablative polymer matrix with heat dissipation nanoparticles, are applied to Starship, the heat shield's durability will become incredibly robust. It will be able to safely protect the spacecraft not only from the extreme heat generated during Mars' atmospheric entry but also from the harsh conditions of outer space. This concludes our fictional exploration of enhancing Starship's heat shield. Although these are currently imagined scenarios, we sincerely hope this creative thinking will inspire all researchers and developers exploring the universe. We express our deep respect to everyone who is working tirelessly towards the great goal of space exploration. Visualizations of the technologies introduced today will soon be shared as images on our community page. Please check them out if you're interested. Thank you very much for watching this long video. We will continue to support SpaceX and Starship's development, and we encourage your continued interest and support for humanity's relentless pursuit of space. With your passionate interest and support, we can fly further and higher. Thank you.